Hello there, Mr. Sutton bringing you this lesson on the integral and p-series tests, which we will be using in this lesson to determine convergence. We're going to begin this lesson with a flashback to the harmonic series, 1 over n. We tried figuring out whether this converged or diverged. We tried the nth term test, but the limit as n approaches infinity of this bottom-heavy function was 0, which told us nothing other than that it might converge. We tried the ratio test. We had 1 over n plus 1 over 1 over n, so nth plus 1th term over nth term, and we found that that was really n over n plus 1, but the limit as n approached infinity of that was just 1, which again was inconclusive. So what now? Today we're going to figure out what. So our next test that we're going to be using comes from an interesting observation about series, which is that a series is basically a Riemann sum or a RAM of a function. If I have some series with f of n as the nth term, this is equivalent to taking a Riemann sum of the function f of x. Basically, every time you move up through these n values, you're moving to a different rectangle. Every time you plug in 1, 2, 3, you're getting the height of one of these rectangles. So this sum in these rectangle areas basically mean the same thing. Now, the area under a curve can also be found using an integral. Since integrals and these series are both talking about the area, that means that a series is going to behave the same way as its corresponding integral in terms of converging or diverging. So this observation about the connection because of these areas leads us to something called the integral test, which says that if you have a function that is continuous, positive, and also decreasing, so basically something that's going down like this without any breaks in it, then the series from that function and the corresponding integral of that function are either going to both converge or both diverge. Now, how you would use this is if you know the integral converges, you also know the series does, and same with diverging. Now, there's just a few notes here. One is that these lower limits are both going to have to match, and the other big thing here is that the integral test doesn't actually give you the sum of the series if you needed to find that, because an integral gives you the exact value under the curve. A series gives you essentially a RAM of the area. So as long as you keep this in mind, this can be a very powerful technique. So let's take the integral test for a test drive. And in general, your series with ln of x tend to be integral test questions. I mean, we've got 4 more tests I'm going to show you down the road. None of them is going to work for ln functions. So this is a good one to have in your back pocket for situations like this. We're going to start by stating that we can actually use the integral test, which means we have to state that the function is continuous, positive, and decreasing. So for this one, we would say 1 over n ln of n squared is continuous, and by the way, it's not, at n equals 0 and also n equals 1. Both of those are going to zero out your denominator and cause all sorts of troubles. So when you're stating this statement, you'll also want to include the interval. So I'm going to go back here and say for n greater than or equal to 2, this function is continuous because at 2 we don't have any asymptotes. It's also going to be positive because if you're plugging in 2 and numbers bigger than that, you're just taking positive numbers and keeping them positive. And it's also going to be decreasing because your denominator keeps getting bigger and bigger as we go. So given all this, we're allowed to use the integral test. Okay, so how do we actually do that? We're going to set up and evaluate an improper integral, because we're going to infinity here, for this series. So we're going to have the limit as b approaches infinity of, and we're going to have an integral from 2 to b. Now the 2 is here because we have to match the lower limit of summation for our series. Inside here, we're just going to have this function, 1 over n ln of n squared with a dn on top here. All right, so we've got an improper integral. If you're feeling up for it, pause the video and see how far you can get to evaluating this. All right, so let's see how that went. This one's a little bit tricky, not a one-stepper. You might notice that we have an inner function whose derivative, 1 over n, is also in here. So this is a good candidate for substitution. I'm going to let u equal ln of n, and then I'll have to figure out dn and swap something for that eventually. So if I take my derivative over here, I've got du equals 1 over n dn. And then multiplying both sides by n, I have n du is equivalent to dn. so that's nice. I also have to swap out these limits of integration. If n equals 2, u is going to be ln of that, ln of 2. If n equals b, then u is going to be ln of b, so that's not too bad. Plugging all that back in, I've got the limit as b approaches infinity of the integral from ln of 2 to ln of b. And then inside, dn gets replaced by n du, and instead of ln in here, we're having a u that's being squared. Okay, now the n's are going to cancel, so we have 1 over u squared, which I can rewrite as u to the negative 2, make it a little easier to use my reverse power rule. This bumps up to an exponent of negative 1. Dividing by that, I have negative u to the negative 1, evaluated from ln of 2 to ln of b. Plugging things in, this is really negative 1 over u, so this is going to be negative 1 over ln of b. Still have that limit as b approaches infinity, and we're going to be subtracting the negative 1 over ln of 2, so adding 1 over ln of 2. Now, as b goes to infinity, this first bottom-heavy function is going to go to 0, leaving us with just 1 over ln of 2. All right, hopefully you got that far, but if not, that's okay. You know, we're just reviewing this stuff. But now, at this point, we have to state our conclusion of whether this converges or diverges. And again, we're basing that on whether our integral converges or not. Since this integral converges to a number, we would then say that our series converges by the integral test. And now it's time for a rematch with the harmonic series. Use the integral test and see if you can figure out whether this converges or diverges. All right, now hopefully you remember to state the conditions of our integral test. This 1 over n function for n greater than or equal to 1 is continuous, positive, and decreasing, so we can use our integral test. So setting up our integral, we have the limit as as b approaches infinity of integral from 1 to b. Again, the lower limits have to match here, of 1 over n dn. Antiderivative of this, we can take that right away. That's going to be ln absolute value of n, evaluated from 1 to b. So that's going to be, since these are all positive numbers here, because we said we're greater than or equal to 1, that means we just have ln of b minus ln of 1 inside this limit. Well, ln of 1 is just 0, and if b is approaching infinity, ln of b is approaching infinity. So this whole integral goes to infinity, diverges, so we can then say that 1 over n diverges by the integral test. So the good news is you finally figured out what the harmonic series is doing. The bad news is this is kind of a drawn-out process, but there's more good news. On the AP exam, if you identify that a series is the harmonic series, you can just say it diverges without any further proof. So it turns out the harmonic series that we just dealt with is a special case of something called a p-series, which is just a series that can be written in the form 1 over n to the p, where p is some constant like a 1 or a 2 or even some kind of fraction. Our question on this page is, for what values of p will a p-series converge or diverge? Is there an easy way to tell? We're going to use the integral test to analyze this. So let me set up my limit as b approaches infinity of the integral from 1 to b of, and now we have a general case, dn over n to the p. Now to make this a little bit easier to integrate, I'm going to make this n to the negative p, and now I'll use my reverse power rule. So this exponent bumps up to negative p plus 1, or I could write this as actually 1 minus p, and then I have to divide by that. So I'm going to be evaluating n to the 1 minus p over 1 minus p from 1 to b. Plugging in my limits of integration, I've got b to the 1 minus p over 1 minus p, minus, well, I just have 1 to something, so that's just going to be 1 in the numerator over 1 minus p. And now we're going to see what happens at different values of p. So the key here is all the action is happening around p equals 1. If p is less than 1, let's see what happens with this exponent. So you'd be doing 1 minus something less than 1. That would give you a positive exponent, which means that this b that's approaching infinity would stay in the numerator. Well, if infinity is in the numerator, then this whole thing's going to infinity, which makes our integral diverge. Now let's say that p is exactly 1. Well, now you're just doing 1 minus 1 in the denominator, which is 0. So that would also cause your integral to diverge. And if p is greater than 1, Now you're doing b to the 1 minus something bigger than 1. That's going to give you a negative exponent, which means that your infinity has a negative exponent, which means your infinity is going down to the denominator. And if that's the case, a constant over infinity is just going to go to 0, which is going to cause your integral to converge. So this all leads us to something called the p-series test, which says if you have a p-series and your p-value is either less than 1 or equal to 1, less than or equal to 1, that's going to cause your series to diverge. And if you have a p-value of greater than 1, we can say that our series converges. And now, armed with the p-series test, we're going to tackle these last two problems, which would take us a lot longer with the integral test. Pause the video and see if you can use the p-series test to get to the bottom of these. All right, so on this first one, we recognize that we have a p-series with a p-value of 6. Since 6 is greater than 1, we can conclude that this converges by the p-series test. Wow, that was quick. Let's do this next one. I'm going to rewrite this to be 1 over n to the 1/5. And I see then that I have a p-value of 1/5 for a p-series. Since that's less than or equal to 1, we can say that this series is going to diverge by the p-series test. This concludes our lesson on the integral and p-series tests. Till next time, Mr. Sutton signing off.